各位师长、各位学长姐、各位学弟妹，我也是今天早上才认识他。我今天早上用我残存还记的德文跟他聊了10几分钟，现在已经到我德文的上限。我很开心今天在这边为各位介绍这个Schaer 先生啊，他是从瑞士巴塞这个地方来的。他本身不是牙科医师，他主要是在做骨科生物力学研究的。那他曾经是 ITI 公司植牙研究部门主要的负责人。那他现在后来离开 ITI， 他现在是 Camlo 公司的主要的老板，也在欧洲成立了一个叫做巴塞口腔重建基金会。那他刚刚跟我讲，就这个重建基金会呢，每年其实都有一些跟植牙相关论文的竞赛，只要是英文 publish peer review 的 input journal article 被 accept， 都有机会可以去竞争啊。第1名的话可以拿到1万块钱欧元啊，也是不少的费用。So today it's my great honor. I speak English now. Is it okay?
Yeah.
I think my German language is already beyond. So let's also welcome Dr. Alex Schaer. It's not so easy to pronounce. Correct?
Yeah, very good.
Welcome.
Thank you. Oh, perfect. Thank you very much for coming, big audience. It's a great honor to me to present to you my experience. I have for like over 25 years. Like I said, in 1993 I started at Straumann developing endodontics, and then I worked my way up to head of R&D, like the synopter connection at tissue level, the solid abutment system, SLA surface was all under some of my leadership. And then I looked for a new challenge and started with Camlock 2003 until 2016, when I took full-time over the foundation, because the Oral Reconstruction Foundation, Camlock is owned by Henry Schaer, one of the largest dental company in the world, if you look by revenue, and they also have some other implant companies like BioHorizon, and they needed to have an independent foundation. Nowadays, because with all the anti-corruption law, etc., it's very important that the foundations are independent, so we completely, I'm independent as long as we get money, but I'm also in the advisory board of Camlock and some other companies to help them. You know, they build up on my experience. There are not so many people around because implantology is not that old to have like over 25 years in experience. This presentation, a very similar one I gave at the New York Academy of Prosthodontics, and you know, it's not about clinics. I'm an engineer, originally electrical engineer, then bioengineer and biomechanics, and it's about the implant abutment connection. So I will, maybe it's good if I see here. My agenda, like the introduction, then the factors influence the implant abutment connection, then the visualization of the microgap in a conical implant abutment connection, also the influence of cyclic mechanical loading on the implant abutment connection, and then the mechanical testing of implant abutments, and obviously very important, the conclusion. So this is a histology through an implant with the abutment. This is a titanium implant and a ceramic abutment in it. And the implant abutment connection is the interface where we have the interruption of the form continuity. If you look mechanically at it, it's the interruption of the mechanical continuity. It's where the interruption of the material continuity, because sometimes you have different materials mating each other. It's the connection to the inter-implant gap spaces, and all these concerns the butt joint as well as the conical connection. One of my hobby, apart from traveling, is also taking pictures, and this is done in the Amazon, and I use this as analogous. Oh,
it's better.
It's better. It's not working. Do we need it? Yeah. Okay, better. So you have to look very carefully at the implant and the implant system and the abutment to see the difference between the different systems. It's like in this picture. You have to, if I enlarge this before you sit on that trunk, you better be careful, because there is a tarantula and you don't sit on that. So please look carefully at the implants and the abutments you're using. So there's a lot of factors influencing the implant abutment design. It's the connection type, it's the material you're using, it's the indexing, how you index, like how you transfer your implant position to your master model, either conventional way or digital, doesn't matter. And it's the dimension of the implants and the wall thicknesses, etc. It's the tolerances in production, and it's also the manufacturing, how you can manufacture something. And then manufacturing is one side, it's also how you control what you manufacture. And then patents. In the early days this was a very important thing, because there was like some Americans who sued like everybody, and there was heavily involved also in patent litigation. And all these play a role in that. For me, is the ideal implant abutment connection. And as I show here the gears, it's like a big Swiss watch. Everything has to be precise, and everything has to have the right dimension, that you get a working system at the end. So let me first talk about the connection type. Basically we have two variations. One is called parallel or butt joint type, where the abutment makes contact to the implant at the top level, and the conical, where the abutment connects to the implant, where the mechanical force transmissions happens in the conical part. People ask me, why don't you make something, where you have best of both worlds? Unfortunately, this is not possible. Mechanically, you never can have contact here and here, like up here and here. Always one point will make contact first. And so it's not possible. You would need infinity accuracy. Here, like this also from the earlier days, like some finite element analysis. On the left side you see a butt joint connection with additional Bonnet mark. And this is like the cone, the stromal tissue level implant. Here you can see that the abutment screw has a lot to take off the load. The implant is loaded from this direction, and you have very strong tension and compression here, and you see the lift off of the abutment. That's causing the screw loosening or breakage. Where here in the cone you have less stress in the screw, in the abutment screw, and a lot of the stress is taken through the conical implant neck. Here is another type of connection. That's what the camlog is known for, the tube-in-tube connection. You can see that tube, it's like, it comes from the car design, where you have your windscreen and you have like two tubes in it. It's very strong because of the principle of tube-in-tube, and the abutment screw is less because you have here contact. The dimension and the tolerance, so how much do they influence it? As I say, when you manufacture something, you always have to give tolerances to it, because nothing is absolute. And for example, if you have a 15-degree cone and you change that cone just to, it's half a degree less, like it's 14.5, then this abutment sticks further out 178 micrometers. If the cone gets smaller in the implant. Otherwise it's vice versa. Or another things, like if you have the 30 degree, like the stromal tissue level implant, and that cone changes half a degree, it's less critical. It's only 88 micrometer. But for me the ideal is the self-locking cone, which is around between 11 and 12 degrees. It depends on the coefficient of friction between the materials. We also did, when we developed the cone lock system, a very extensive finite element analysis. For those who don't know finite element analysis, you divide your mechanical structure in little cubes or tetrahedrons, and these you can mechanically describe. It's very important that you have fine mesh where you have transition because of the notch factor, and we used 135,000 contact points, meaning for the next picture you see you have to solve non-linear equation with over 400,000 unknown. So here, like we simulated the standard, the ISO standard for testing dental implants says you have to load it 30 degrees off axis, cyclic loading, but you also have to assume 3 millimeters bone resorption from the nominal bone level. So that's where the implant was embedded up to here, embedded in the computer. So this is the situation with a perfect matching cone, because quite often you see in those models everything being perfect matched, and in reality it's a different show. Here is when the bone is at the up at the nominal bone level, no resorption. You see there is less stress on the abutment and the screw. Here is, for example, the same when we simulated how does it happen if you have a cone discrepancy of half a degree with bone resorption and with no bone resorption. It just gives you a bit an impression how those tensions progress, but I don't want to bore you too much. With nowadays finite element analysis, with modern things, you also can calculate the micro gap, and here you see the fourth situation, how the blue means full contact, and where you see the color, and there are also denoted the maximum micro gap you had, like here in this situation, 6 microns or 5 microns here is no, and you see when you have no bone resorption, so the things are better. The manufacturing and quality management, just to address that quickly. If you have to manufacture something like this called the tree lobe or the noble replace connection, it's very tricky because titanium is very tough and you have a fine mill, which is, you know, like if this is about 3.5 millimeters, this may be 1 millimeter or less, and this pushes it to the side. For example, in a connection like the cam lock connection, everything is milled, is laced, except what I have here, the red section has to be milled out. The rest is laced, so it's higher precision you can achieve with that. It gets a different story also if you look to the inside of the implant, the inner configuration. This has to be milled all the way out of the material. It's quite complex, also complex how to measure. In the cam lock, in the cam groove connection, you only push the groove out. Another question is, how do you measure that thing? Like in the abutment, you can actually measure it, you project it on a screen, or you do it nowadays with video and video measuring robots, you can analyze it. But in the implant, it's not easy to measure. You would have to make a cut, and the cut would have to go perfectly through the axis to get the right axis. We find the solution within with some high tech around the area, and also within the watch industry. They measure the airflow within a connection like that. And this guarantees you can scan, therefore, the whole dimension of the cone, because it's very important that you have the precise manufacturing. And we had this specially developed this machine, which had an accuracy for 50 consecutive measurements of 1 micrometer, of 0.1 micrometer, or 0.034 degrees. So you could really prove that your cone had the right dimension. The indexing, it influences also how you transfer your position from the implant to your either digital, as I said nowadays, quite a few times, and or conventional. We have done, like the University of Professor Nelson at that time in the University of Schaer in Berlin. She put in a block implants embedded in a steel block. They were like 0D perfect, perpendicular, 5 degrees off, 15 degrees off. She added on the abutment this measuring device with about 34 measuring points. The whole thing was analyzed by a measuring robot, and from out of that she calculated the rotational error. If you place the same abutment in and out again for 50 times, and also the vertical discrepancy and also the tilt. And these are the results. When you hand tight it, you see like this tissue level like 3.3 degrees, 4.9 the Astra, that was the maximum, Noble Active 7.2 degrees, quite a lot of rotation replaced. The one I showed you is the minim 4.5 degree. And here you see the superiority of the cam groove connection. That's something which is also used in other mechanics, in machine industry. It was with the cam lock 1.5, 2.1. Also shows the precision we have in manufacture. Ankylos is that very thin, was 6.3 degrees, Straumann bone level 4.5. The story looks a bit different if you talk it to the recommended torque of the manufacturer. Astor went up to 6 degrees, Straumann had 2.8, which is also good, and we only had at that time, they only looked at the conical connection because there is really more critical how high you torque it because of the, it seeks into the cone. At 2.8 and Camel 1.6. Also the vertical discrepancy, the range was from 20 micron or 15 micrometers Straumann to 43 with Astra when you hand torque it, and with the torque there is a big difference, as you can see, 113 micron, 144 with Straumann bone level. That's because you torque it to 35 Newton centimeter. Cone lock you torque with 30 Newton centimeter. These were all maximum values, not average. And the ankylose was only 15, but this was 50 Newton centimeters, so that's why they had such a good result in this. You also can calculate that with a bit of geometry, but I don't want to bore you with that thing. They also published a study where they assumed the theoretical microgap or the gap through tolerances and compared it to the theoretical things, and they could show that the cam groove connection was the one which was closest to the ideal. People may ask why you don't need these things, this accuracy, but if you want to do something like some extreme things, they do sometimes also in German, like this full zirconium frame, you really need precision, otherwise you have a problem when you put it in the patient mouth. That's how it looks, the final work. I got this from a Brandelshof and Carcacci clinic in Munich, and the deputy technician was Jochen Rotz. This is all published in peer-reviewed journal. This is the reference list of it. Some of them are open access, and quite a few of this work is also supported by the foundation, at that time the Cameron Foundation. The material, I was wondering what happened if you collect in the finite element analysis, like that's the model we had. I just replaced the mechanical, I did it, I'm not the expert in finite element because you have to do that full time, that you get really good results because it's so complex. They replaced the material properties of the titanium with ceramic, and the results, the question is, do you really need ceramics? Because like when I look at the study, I got this from Irena Seiler. She's now in Geneva. She used to be in Zurich in the team. And after 5 years, she said, yeah, maybe 5-year results of randomized clinical control comparing zirconia and titanium abutment support single carotid canine posterior region. She concluded there's no big difference, but she said, when you look at the picture, maybe you see some gray staining. You see it better on the original, but on the screen there might be some gray shining through. There maybe the ceramic abutment would be an advantage. But if you have a situation like this where you have really severe soft tissue resorption, I don't think a ceramic implant solves the problem. You have to make a connective tissue graft to get a nice result. So when these are the results from the calculation. At the top on the left side, it's titanium and ceramic here, and you see the max. Don't compare it like, red means very high, but there's different scales between the two sides because we really had to scale to see something. So the maximum stress in the titanium was 811 and 825 with 300 Newton, where with 200 Newton, like we already had 2,269 megapascal and 3,500 with ceramic into titanium. And if you look at the equivalent plastic strain, titanium can, take it easier than what's possible to do with ceramics. They can't be formed, it just breaks off. What can happen, I got this picture from Professor Boyer from the Charité. He showed at the Congress and asked him because if I can have it. We also work together. That's the Begos German system. They have like a bevel and a hex inside, and they have full ceramic abutments. And this was with a monolithic all ceramic abutment after 2 months in clinical service. The hex was almost completely worn out. You couldn't see anything. And just we had 2 weeks ago, we had a congress in Austria. Another Dr. Gagacci was showing this slide picture. He said, you know, after 2 years, the patient came back and said, oh, my crown is loose, it has play. And so he took it off. And this ceramic abutment, we don't have in the product range ceramic abutment. This is a copy in ceramic of an original camlock abutment. And there was a lot of, he said, you know, debris from titanium. Near the implant, he already sucked it off. But if I look at the cam groove, I see why they have played. It's almost worn out. So that's not really good if you have this material connection. Another study, a pilot study from the University of Freiburg, where they looked at metal elements in tissue with dental peri-implantitis. The objective of this study was to investigate the incidence of metal elements in bone and mucosal tissue around dental grade 4 commercial tube titanium implants with signs of peri-implantitis in urine patients. That's how the situation looked like. There were anyhow like patient with peri-implant and indication for explanation. So they took like hard and soft tissue sample around the implant at the place, and they analyzed it histologically, and they could find, you know, metal element in the soft tissue. They also did a very extensive analysis with synchrotron radiation, X-ray fluorescence spectroscopy, line scans for the elements titanium of each sample, and in 75% of the sample showed clear signs of titanium. They also did the area scans for calcium, phosphor, titanium, iron in the soft tissue. They could find that too. Their conclusion is titanium iron elements were found in soft tissue and hard tissue retrieved adjacent to implant showing peri-implantitis. Not only macrophages were detected in the tissue with increased titanium concentration, but also lymphocytes could be found. Further study need to clarify whether there is a correlation between the amount of metal elements and the specificity of the immune reaction induced in dental peri-implant tissue. Understanding the molecular pathogenesis of peri-implantitis may lead to adjunct drug therapy. There are additional studies who also look at the wear of titanium zirconium implant abutment interface. A pilot study, for example, done at University of Connecticut, and you could actually clearly show much more wear with ceramic titanium combination than titanium, or another one done at University of Munich, where they looked at the wear with micro CT and how it wears the contact area off. I think the solution to that is that you use those titanium bases where you originally manufactured abutment, and you make your meteor structure and your rounds on top of those titanium bases. This is a very nice case done by Professor Belser when he still was in Geneva. When I was on that trip in South America, I also visited in Peru, Machu Picchu, and I was astonished, you know, when you get these old structures being maybe built in the 14th century, and you see those granite blocks, they're like tons, heavy tons, like they're that big from the ground, or even bigger, several tons heavy, and they could, and they're not perfect, you know, flat or something, but you couldn't stick a knife in there, not possible. Took out my Swiss Army knife, but it didn't fit in there. So I was thinking, and we play about microgaps with this, nowadays with implants and the buttons. And at the beginning, there was this guy from the University of Frankfurt, Holger Zipper. He went around and said, you know, the butt joint connection is not good because it opens up and you have a microgap, and this was his proof. You don't have any microgap if you use a conical connection. This is actually the ankylose, and it caused me a lot of headache at the beginning because, you know, camlock was a butt joint type connection. But, you know, when you went into the literature, they did analysis where they placed bacteria, so endotoxin, in the dead space below, in the hollow space, the space in the apex of the inner connection, and they could demonstrate in all the systems within a few days they penetrated through into the solution the implant was in. And then we also were fortunate with Katja Nelson, at that time still in Berlin. She started to use synchrotron light source with some physicists. She had some connection, and to analyze, to X-ray, something like X-ray the implant abutment connection. The thing is about these machines, you don't just have it in your backyard here. There's only about 50 of those in the world, and each one costs around $100 million US. So you see how big it is. I mean, you need some more space back there. And the way it functions, you have an accelerator where the beam is accelerated more and more, and then it's deflected in those measuring chambers. And there where you can analyze your implant and abutments to see what's going on. That's the team. This is Professor Nelson. That's one of her students or assistant, and these are the 3 physicists. And we might be lucky to get into this institution measuring time maybe 3 o'clock in the morning when you come with your dental implants. It compares like a candle, like the first picture I showed you from this X-ray from this Mr. Zipprich, and to the energy of a galaxy. So it's like looking at a candle at the implant abutment of this high energy. And the way it's done, as I said, it's accelerated the beam, and then it's this hard X-ray getting to the implant abutment, and you X-ray it and you analyze it in the computer. Knowing the geometry, the physicist could also improve the accuracy or the resolution down to parts of micrometers, because you know it's either elliptical or round, so you can assume some of the physics. For the first time, they published the microgap, and here you can see an unloaded system. But if you look at here, that's the abutment screw. It's the abutment, it's the implant. You can see here the gap where before you couldn't see anything. And it's quite a different story if you load it, the implant, and do the analysis. You see the microgap more pronounced here, it opens up. If I enlarge that, you see on the left side unloaded, loaded, it's quite different. And also that's the Straumann, I think it's 22 microns it opens up, but here bad thing is it opens up all the way through, and the ankylose only at the top. And then they did also first fatigue load the implants, and then they measured the implants. And this on the left side, for example, the ankylose without fatigue load, and with fatigue load. And you know, fatigue load 120 Newton at 30 degrees, 15 Hertz, 5 million cycles, that's what the standard says. And what they could detect here was a microgap. They resolved that. And there's the theory that, you know, some of these microcracks or the plastic deformity of the implant maybe also have a course onto bone resorption. I took all the literature I could find and the measurements from them, and you know, it's the 4 points where the microgap was measured, and it was before fatigue loading and after fatigue loading, and that's how the results look for the bone level implant. I would say it's good, very good. It's 0.2 to 0.7 or 8. The ankylose was not that good. It opened up. Very bad was at that point the ankylose plus. That's probably the one with the crack. That's why it's so bad. Astra, I didn't find any measurement. No, they said it was 0 at unloaded at here at the shoulder, which can be true. And this was after mechanical load with 200 Newton at 30 degree loading, and the picture looks quite different. It's up to 25 microns opening up the gap. Another study they also did with the synchrotron. The objective of this study is to analyze and visualize the microgap size after cyclic loading and the wear pattern regard the implant abutment connection design, and so you'll probably be interested in that. So they took synchrotron picture at day 0, or no loading, 100 cycles, and then they took again pictures with the synchrotron, another 100,000 cycles, they took pictures again, and then they did the 800 cycle and the final analysis. That's how they loaded the implant abutment complex. And here, that's the fourth system they analyzed. It's the Ankylos system. I think it has a 6.7-degree angle. The Astra system here has an 11 angle, and you see also the height of the connection. It quite varies. Here, for example, the Noble Active, I think they have 15 degrees, not quite sure right now. 15, this I'm definitely sure it's 15 degrees. The Straumann bone level, but a very short conical connection. So what they could say, the median gap size, you can see after 200 million cycles, that's where you have the biggest change afterwards. That's in the upper part of the connection, and that's in the lower part of connection. After about 200 cycles, not much changes again, but you have some change at the beginning. They also took scanning electroscopic pictures and analyzed the connection. And I just go quickly through each one. That's the Ankylos connection, how it looks after 200,000 cycles at 98 Newton. They loaded with 10 kilogram, that's equivalent to 98 Newton. There's a low amount of wear particles and minor tribolayers. If you go after 1 million cycles, there is greater wear and clusters of material. And this is obviously just below where the abutment becomes obvious above the indices below the end of the implant abutment melting zone. They had piles of abrasive materials which had a height of 5 to 20 microns, and some plastic deformation and some chipping you could also see. Looking at the Astra OsseoSpeed 4.5 millimeter implant, they had those patchy tribolayers, some plastic deformity, the yellow arrows, and some scratches. When you enlarge that, the scratch area showed that part of the scratch result from the mating procedure was clear evidence because you went through those tribolayers through. Also, within the tribolayer, they had a high amount of wear particles can be found, some of them embedded in those layers. Now the Noble Active at 1 million cycle at 98 Newton. There was some wear, appears localized at the mating surface, and some tribolayers from friction. It's less pronounced but shows signs of threading wear. Chipping of pure titanium at the index and the lower edges of the mating zone. And the bone level implant at 50 times magnification, islands of tribolayer on the conical mating surface. If you enlarge that, the tribolayer present with a maximum of 28 micrometers and embedded wear debris. The index showed the crack at the very bottom, which will result in chipping of the particle. If you enlarge the crack at 5,000 times magnification, it looks quite dramatically. The conclusion was the microgap at the interface of unloaded titanium dental implant abutment, the same as exists prior to cyclic loading, and is enlarged after cyclic loading at 98 Newton for 1 million cycles. The highest inclination of increase of the microgap was seen within the first 200,000 cycles. Thereafter, a gradual increase was observed. The implant abutment interface showed different mechanisms of wear comprising threading, adhesive wear in all implants examined regardless of their conical interface design. The mounting medium of the implants might influence the wear behavior. They went a step ahead and they designed a machine where they could, within the synchrotron, load the implant. That's the apparatus they designed. And they took like the scanning X-ray pictures so that they can analyze more precisely in 3 dimensions what's going on. You know, like that's a 3-dimensional visualization of the implant abutment connection microgap superimposed on the CT scan of a dental implant. This is, for example, the Noble Active on the 333 Newton cyclic loading. having a large gap to a small gap. And this is, you know, when you compare to the pictures or the movies I showed you at the beginning, it's unbelievable this resolution they can achieve with this synchrotron radiation. And you see the implant was loaded, the gap opened here up in this trimer bone level implant, and then they release the load, but it doesn't close completely. And you also see some deformation in the neck area. One of my last studies I would like to show you, the impact of force transmission on narrow body dental implants made of commercially pure titanium and titanium zirconium alloy with a conical implant abutment connection, an experimental pilot study which was published in the International Journal of Oral Maxillofacial Implants. The purpose of this study was to visualize the mode and impact of force transmission in narrow diameter implant with different implant abutment design and material properties to quantify the displacement of the abutment. Here shows how the specimens were embedded. And here is for the evaluation of the changes of the outer diameter of the implant shoulder. The measurement points of the Astra implant and the Straumer implant were subdivided in two regions, like the upper and the lower part. Here you see Straumer and up here the Astra. The Astra I think is 3.0 millimeter and the Straumer is 3.3 millimeter in diameter. And you can clearly see when you load it from 0, you load it up to 125, 250, it doesn't go back to 0. The gap remains. And also intrusion, it doesn't go back to its original position. Here is a bit more, also more visualized. For example, the synchrotron radiography pictures at different stages, force application of the force with 30 degrees to the implant axis. The red line is the reference line, like here is 0 loaded. We don't see anything, and then it's loaded 125 Newton at 30 degrees here. It moves up and a little gap opening. The gap is getting bigger with 250 Newton, and it doesn't move completely back, and the gap doesn't close when you unload it. Here is the comparison on top if the commercial pure titanium grade 4 versus the rock solid. You know, it's rock solid, does it behave a bit different because it's stronger but it's less elastic, and you can see the deformation. Here's unloaded 250 and the gap remains open, and the same with the rock solid. It also happens like this. You know, here it's always the same line. That's at 200, at 125, 250, 0. Say you have some plastic deformation. So you really should be careful. Narrow body implants with a conical implant abutment showed a deformation of implant shoulder during loading, independent of the implant body material, when incremental force application up to 250 Newton at 30 degrees was applied. Deformation of the implant should persist after the load is removed. Narrow diameter implant body is made of titanium zirconium alloy. Trade name is rock solid. Did not show less deformation of the implant shoulder upon loading, but rather similar behavior to narrow diameter implants made of commercial pure titanium grade 4. During load application, an angulated intrusion of the abutment into the implant can be demonstrated, which persists after removal of the load. And at 250 Newton of force application, a permanent plastic deformation of the implant shoulder, which has about a thickness of 0.3 to 0.4 millimeter, occurs in diameter implant with a conical implant abutment connection. All these things are also published in peer-reviewed journals. Some of them are open access because, like the Journal of Synchrotron Radiation, it's not so easy accessible at the university or even private clinics, even more. I didn't show you the cone lock in these things, but we used, because it wasn't available at that time, we used that technology, and I could give a very few samples to analyze, and this was before the optimization. We also had a micro gap of 0.8 to 6 micrometer. because we had an idea that we want to have contact always at the upper part, and after the optimization we had 0.4 to 0.8 micrometer. There's another study where they looked at the mechanical behavior of different implants like the Astra, Bego, Camlog, Freeatent, Ankylos, Novel Biocare, and the Straumann standard implant, talking tissue level at that time. And that's when they statically loaded the maximum forces they could achieve with the deviation of the different samples. And you can see at that time the parallel wall were stronger, but after a million loads with 100 Newton at 2 Hertz, there was not much difference in the behavior of the system. Because like we have the Camlog and Conlog system, which has more or less identical outer shape. The only difference is that bevel up here, I could plot, for example, because that's the ultimate test, is the fatigue load curve. And this is not Newton, it's scaled in percent of the maximum. So the butt joint, if you think that has 100%, the conical connection had 25% stronger. And you have to, by this, for the registration, etc., or the authority, you have to get the point where you don't have any breakage for three consecutive measurements. And each of these measurements, if you go for 2 million cycles, it's 11 days at 2 Hertz. You shouldn't go too high. The experience showed if you go higher than 2 Hertz, the mechanic behavior of implant abutments, it doesn't go back into the right position, and you get a big variation of the results. We also have, like out of our foundation, at that time it was called Camlog Foundation, we organized a consensus where we looked at the impact of implant abutment connection, positioning of the mechanical collar, microgap and platform switch, and Kessel bone level change. It was published in Clinical Oral Implant Research, and it's open access, either from Millie or also on our foundation homepage, which is www.orfoundation.org. And just to give you a very few of the results, like the consensus statements regarding implant abutment connection, the impact of the implant abutment connection lacks documentation and may not allow for any robust conclusion, because they did a very extensive systematic review, looked over 1,000 publications. You also, these are open access, these systematic review which go with the consensus. And second crestal bone remodeling has been observed for either internal and external or conical and butt joint connection. Some evident success that microbial leakage may occur irrespective of the design of the implant abutment connection. And the clinical recommendation regarding the implant abutment connection is the clinician is advised to choose a stable implant abutment complex to minimize the potential impact of the micro movement and micro leakage on crestal bone remodeling. Now I come to my conclusion of the whole talk. The nature of the geometry of the implant abutment interface and the manufacturing tolerance influence the lack of accuracy. Commercially available implant abutment connection are less precise than advertised. Plastic deformation at the implant abutment connection is evidenced at cyclic loading with a force as low as 98 Newton and 120 Newton. I found in the publication also through own measurement. The mechanical strength of narrow diameter implant is reduced, therefore this implant should be used with caution in areas with higher forces. All investigated conical implant abutment connections show the continuous micro gap regardless of the design and the amount of force applied. All conical and butt joint connections have advantage and shortcomings. The mechanical influence of different materials in the implant abutment interface needs to be investigated more thoroughly, and what happened out of that. And my take-home message, this is my famous income wall, is the take-home message: the myth of the ideal prosthetic implant abutment connection is busted. There is no ideal implant abutment connection. It's very important that when you do the engineering, challenge is to optimally combine and engineer the factors influencing the implant abutment connection for the best connection. I still have some little time, so maybe do some advertisement for the foundation. We have a big congress next year in New York from 30th of April to 2nd of May. We also have a poster competition. The first 30 posters are selected. They have free entrance to the congress. The foundation, and nothing to do with the congress, we give out, you can apply for grants twice a year. Everything you find on the homepage. That's actually the homepage address, www.orfoundation.org. And also this, at the Congress, every 2 years we give out the Research Award. So far, deadline 30th of November, it's a bit late, but we would appreciate if you get more. The criteria are described on the homepage. It doesn't have to be Camlock or BioHorizon or anything. It has to be published in a peer-reviewed journal, and it has to be in English. And the first prize is €10,000, which is quite very big. The runner-up is 6,000, and third place is 4,000. This is the faculty. It's over 45 people presenting at the Congress. We start on a Thursday afternoon. It's on the extraction site management, the aesthetic zone. With Dennis Tarner, Omle Wang, Stephen Chu, and then Irena Seil and Vincent Femer on the One Crown, One Time concept. This is also on the homepage. You can download. Then Friday morning, state-of-the-art tissue regeneration, like the clinical benefits for LPRF in tissue regeneration with Nelson Pinto, Mark Carini. Then Bach Lee, Marcus Steinpad Allen on soft tissue grafting with allografts and xenografts. In the afternoon, we have long-term sustainability in implant dentistry with Thomas Linkevicius, Katja Nelson showing some of the results which I've showed you here. And Michael Picos, Testori on immediate treatment concepts and in compromised sites. And on Saturday, we have putting innovation into focus, advances in implant dentistry. Roland Jung from University of Zurich, talking about zirconia implant. What are my benefits for the clinical practice? Is there benefits to ceramic implants? Lyndon Cooper. Also, Greg Misch, is there a lifetime an implant for life? And then we have this award ceremony of the Research Award and the Poster Award. You can participate at the Congress. With Mariana Sanz and Tom Taylor in the afternoon as our moderators. We have case presentation, solution for challenging situation. Cases presented to an expert discussion where the experts discuss how they would solve it, and we showed it how we solved it. The audience can participate via app or send or via microphone. With that, I'd like to finish my talk and show you a picture from my home country, the Matterhorn. And thank you very much for your time and attention.